Okay, so now we're going to discuss the second law of thermodynamics. Last time we discussed the first law of thermodynamics, which is essentially a way of stating conservation of energy for thermodynamic systems. But it leaves a few questions unanswered, and that's where the second law of thermodynamics picks up. And so one of the things that it implies is that thermal energy cannot spontaneously transfer from a region of low temperature to a region with a higher temperature. Okay, and so we're going to look at some of the definitions of the second law, look at some of the implications, such as this one listed, and we're going to look at some of the ways that we can apply this in real life, and some of the ways that this is useful in everyday situations. Okay, so here we have a diesel engine. Now, how a diesel engine works is essentially we have fuel gets injected into this chamber right here. And what happens in this chamber is a process called combustion. The fuel combusts, and as a result of this combustion, high pressure gas gets pushed against this surface right here. This surface is movable, and therefore it rotates this right here, this piston, and what that leads to is essentially that's how the engine runs. Okay, and it leads to rotation, which basically operates the whole system. Now, a diesel engine is something that's known as a heat engine. And a heat engine is a device that converts heat into mechanical work, just like right here. This has heat added to it. That heat is converted to a different type of energy, kinetic energy, right here, mechanical work. Okay, some other examples are steam engines. So this is a steam locomotive. And these were developed around the 19th century, around the same time that the laws of thermodynamics were being developed. And one reason that the two of these developed around the same time was because of this application of the laws of thermodynamics, that you could turn one type of energy, heat energy, into another type of energy, kinetic energy. And so a steam engine led to a lot of advances. It began the industrial age. It led to a boom in manufacturing and machinery, and led to a lot of our modern machinery and things that we take for granted today, such as transportation, large-scale manufacturing, things like that. So it was very important historically in the 19th century. And we also have a refrigerator, and a refrigerator is another example of something that converts heat into mechanical energy. Now we're going to come to this refrigerator and give a bit of a more example of this, but coming back to the mechanical work, we have our first definition of laws of thermodynamics, and that is the Kelvin-Planck definition. What that tells us is that no heat engine operating in a cycle can take in heat from its surroundings and convert it totally into work. Okay, so what that means is that a heat engine operating in a cycle, kind of like this one, it's a cyclic motion, the same things repeat time after time. No heat engine can take in heat from its surroundings and convert it totally into work. And so none of these machines are 100% efficient. Okay, they lose some of that efficiency, and so they can't convert all of that heat energy directly into work. Okay, and this is kind of one of the implications of the first law of thermodynamics, because there's conservation of energy. Energy is conserved, but the change in heat is never going to equal the change in work. Okay, and that brings us to our second definition. So let's look a bit closer at a refrigerator. So what a refrigerator does is throughout this process, or throughout this cycle, what it does is it takes heat from inside the refrigerator and it removes it from the system, leading to a colder environment inside the refrigerator. And it continues to take that heat from the cold environment and move it to a much warmer environment where the hot air is then dissipated. So hot air is taken from a cold reservoir into a hot reservoir. As we see over here, cold reservoir, that heat goes back into the hot reservoir. But we have this little bit of energy right here. And what that says is that all real refrigerators require work to get heat to flow from a cold area to a warmer area. So cold air will not spontaneously flow from heat will not flow spontaneously from a cold reservoir to a hot. Okay, heat in general will flow from hot to cold. The only way that it flows opposite way is if there is work added to that system. And that brings us to the Clausius definition of the second law, and that is that no heat pump can transfer thermal energy from a low temperature reservoir without work being done on it. Okay, so the only way that this can happen, going from the lower temperature reservoir, is if we add heat to the system, add energy to the system for this process to happen. So we now have two definitions of the second law, two ways to look at it, and we're going to begin to move our way towards the third process. And to do this, we need to understand what a reversible process is. So a reversible process is one in which it is possible to return to the initial conditions of a system through infinitesimal changes. Okay, so think of the heat engine, the diesel engine. We had initial conditions before it gets heated. It gets heated, that leads to pressure. The piston pushes down and then it flows back up, and then it comes back down every time fuel is injected. It repeats that cycle. Now, could we ever return to the initial conditions of that system through very small infinitesimal changes? And one way you can do this is this cycle right here, which is what is known as the Carnot cycle. The Carnot cycle is the most efficient thermodynamic cycle that you can have. The efficiency is, in theory, 100%. And so what this consists of is an isothermal expansion, an adiabatic expansion, an isothermal compression, and an adiabatic compression. Okay, so it comes back to a closed cycle. This is our initial condition. We return to our initial condition, and in theory, the efficiency is 100%. No energy is lost within this system. So that's in a reversible process, and we're going to talk a bit about the Carnot cycle in the future. So what's an irreversible process? Well, it is one in which it is not possible to return to the initial conditions of a system through infinitesimal changes. So one in which we make those changes, but we can't get back to the way that initial system was. And that has important implications for work and energy. What are some of those implications? So what does the second law tell us, and what limitations does it give us on physical situations, and how can we apply it to everyday situations, and not things you may see every day, but things that you use every day, or ways that it is helpful to everyday life? One is that it is impossible for heat to flow spontaneously from a cold object to a warm object. Okay, it just can happen. For this to happen, work needs to be done. Okay, so the only way to do this is to add energy to the system for this to happen. Okay, now another way that it's important, if I can go back to this, you can kind of see that from the first law of thermodynamics. Okay, so heat in general will flow from hot to cold, and you need to add work to that situation to get the reverse process. Okay, so if you look at the first law of thermodynamics in that equation, you can see a bit how that comes about. Another implication is that energy spreads out or degrades into less useful forms, and it is impossible to get it back. So in general, energy is going to spread out gradually into less useful forms in ways that we may not consider. And so in physics, a lot of the situations that you consider seem to be perfect situations. So in mechanics, there's no friction. In electricity examples, there's no resistance in the wires or no resistance in certain components. In reality, that's not necessarily the case. And that's what this says right here. So in mechanics, if we have the typical example of a block sliding down an inclined plane, that block will contain, I'll draw just a very small diagram of that. So we have a block. It's going to move down here. Now what happens is that if there's friction, so this surface, these two surfaces are rough surfaces. They're not smooth surface. There is going to be friction. When it does that, So when that block slides down that surface, what you get here is heat. It heats up. Okay? And so energy is going to be lost. Energy is going to be lost in this situation. If I can go back for a second. As friction. So energy is lost as friction when it moves down. Now, let's say 1% of this kinetic energy that the block had gets converted into friction. Now, when this heats up, the particles in the block and the particles in the inclined plane will start to vibrate, and they'll gain kinetic energy, and that's because of the heat that comes into this system. Now, that heat is going to get dissipated to other particles in the surrounding areas until it's completely negligible. So it gets spread out to so many particles that it's impossible to get it back. And so that's exactly what this says, is that energy degrades into less useful forms, and we just can't get it back. Okay, so if we ever wanted to, in the refrigerator, cool down that refrigerator, well, some of that energy is going to be degraded, and it's really, we just can't get it back. It's gone into less useful forms in the atmosphere. And one of the important reasons that the second law developed was trying to find more efficient steam engines in the 19th century, trying to get them as efficient as possible, trying to reduce this degradation of useful energy. Okay, another example is all the air in a room will never go out an open window. So if we have a perfectly isolated room at a certain temperature, which means the molecules have a specific average kinetic energy, if we open a window, those particles are not going to spontaneously just fly out that window, because for that to happen would require an external force. It would require work to go into the system. It would require energy. Okay, so these particles will not be biased to go out the open window. They'll just continue to move around in random motion in a sort of a disordered fashion, whereas if they go out an open window, it's much more ordered. The only way that this can happen is if we add energy to that system. And what it also says is that thermodynamic systems tend to disorder. Okay? And so what that means is essentially, like I said in the previous example, things will become more disordered before they become ordered. So things are going to move around chaotically and randomly. They will not spontaneously have less energy. That energy is going to spread out in multiple ways. Which brings us to our third definition of the second law of thermodynamics. Okay, before we do that, we need to talk about entropy. Now, the second law implies that thermodynamic systems tend to disorder, and entropy is a way of quantifying the disorder of that system. So entropy is a state function that quantifies that disorder. Now, I want you to recall and think back to what a state function is. Okay, so hopefully you've looked it up. At least you know what the state function is, you know its importance. Now we're going to talk about entropy a bit in the future, but right now I want to focus on its role in the second law of thermodynamics. So why is entropy important? Well, the entropy explains essentially why heat does not transfer from a cold area to a hot area, a cold reservoir to a hot reservoir. How does it do this? It gives us this definition of the second law. The entropy of the universe can never decrease. So, the entropy or disorder of a system does not decrease. The universe tends to disorder. So I hope that illuminates a bit about the second law of thermodynamics and you have a better idea. What we're going to look at in the near future are heat engines and what entropy has to say about heat engines and how we can analyze the type of cycles that go on in heat engines. And then we're going to take a closer look at entropy and how else we can apply that to thermodynamic situations.